Welcome to this explainer, you guys. Whether you're a student or just a total morphology enthusiast, we are about to dive into the incredible intersection of abstract math and anatomical body plans. I mean, if you've ever looked out at the natural world and wondered, hey, is there some hidden code writing the rules of biology? Well, you're in for a seriously fascinating ride. So to kick things off, let's think about this for a second. What could an idealized model of rabbit breeding possibly share with the spiraling seeds of a sunflower and, of all things, the segmented anatomy of a common earthworm? It honestly sounds like the setup to a really weird biology joke, right? But the answer actually unlocks one of the most pervasive, fundamental rules of structural growth in the entire animal kingdom. The answer, believe it or not, lies in the Fibonacci sequence. You know the one. It runs 3, 5, 8, 13, 21, 34, and so on, where every single number is just the sum of the two before it. Now, it was discovered way back in 1202 by Leonardo da Pisa to describe rabbit populations. But today, well, we know this recursive mathematical rule actually serves as a fundamental blueprint for self-similarity and optimal growth in biology. It's not just some neat arithmetic trick. It's literally a building code for living tissue. Here's our morphological roadmap for today. First, the Fibonacci blueprint. Second, math in marine protozoa. Third, earthworm segmental anatomy. And finally, a morphology study guide. Let's get right into it. Section 1. The Fibonacci blueprint, nature's secret cellular algorithm. Now, it's so fascinating to frame this sequence not as just some random accident of nature, but as a rigid structural rule. And it's dictated entirely by the step-by-step nature of stem cell clonal development. Think about it this way. When a colony of undifferentiated cells undergoes division, it doesn't just expand randomly all over the place. No, it follows these staggered, iterative cycles of proliferation. And this self-similar recursive network, it naturally locks right into Fibonacci proportions as those cells push and organize themselves into tissues. Moving on to Section 2. Math in marine protozoa. Microscopic case studies of structural perfection. Okay, let's look at some specific external structures, or corticotypes. So these protozoa have these surface ciliary rows, they're called kinetes, and they use them for feeding and moving around. But look at how rigorously they follow the math. Tetrahymena rigidly defends a 21 kinete structure, and that's over hundreds of successive fissions. Paramecium, it holds right at a modal number of 34, and Loxodes exhibits exactly 13 surface kinetes, along with 3 to 5 buccal or mouth kinetes. And the crazy part is, they don't just kind of hover around these numbers. The biology actively resets to these exact Fibonacci states, even after extreme stress like starvation or sexual reproduction. Absolutely wild. Now, take a close look at the contorted kinetodisma of Talina magna. This perfectly shows the physical reality of how these ciliary structures actually twist and organize. You can see that sweeping, spiraling curvature. But here's the thing. That beautiful geometry isn't just there to look pretty. It's the physical manifestation of those recursive cellular division rules, literally pushing the surface architecture into its most optimal energy state. And it gets even more remarkable when we look at the life cycle of this specific organism. As Talina magna actually matures from its encysted immature form into a full adult, its structural complexity undergoes this massive torsion. And guess what happens? The number of ciliary rows mathematically jumps from exactly 21 kinetes to exactly 34 kinetes. No way, right? It literally upgrades its entire body plan from one Fibonacci number to the immediate next. All right, Section 3, Earthworm Segmental Anatomy. The macroscopic blueprint of Lumbricus terrestris. So, zooming out a bit, we can clearly see the metamorphism. That's the repeated body segmentation of the earthworm. In zoology, metamorphism is really one of the overarching principles of body plans. Just notice how the segments look like nearly identical little rings. Well, what researchers have mapped out is that specific segment boundaries, like the exact places where distinct organs begin or end, align perfectly with Fibonacci numbers. Let's navigate this worm's segments like a map, starting right from the anterior, the head. We see a pretty startling pattern. We hit the beginning of the nephridiopores, those are the excretory organs, at segment 3. Then the pharynx and the heart boundary end precisely at segment 5. Moving down, the seminal boundaries hit at segment 8, and the ovaries are located at exactly segment 13. 3, 5, 8, 13. The developmental boundaries of this organism are literally reading like a Fibonacci textbook. The crucial point here is that this pattern continues steadily right on down the body. The all-important clitellum, that swollen glandular band you see on adult earthworms that secretes the cocoon for their eggs, yeah, it ends at exactly segment 34. It's like the genetic blueprint focuses all its mathematical precision squarely on those vital boundaries, while the rest of the tail, well, beyond that 34th segment, it's left largely indeterminate in its total segment count. And hey, it isn't just the outside either. Even deep internally, the math still rules everything. The earthworm's internal anatomy dictates exactly 5 paired hearts, 3 pairs of seminal vesicles, 3 digestive lateral pouches, which are known as calciferous glands, and exactly 3 pairs of nerves branching out per segment from the ventral nerve cord. It is just an incredibly efficient, mathematically reiterative system top to bottom. And that brings us to Section 4, Morphology Study Guide, the ultimate visual cheat sheet. So this visual cheat sheet perfectly contrasts those single-celled protozoa against the macroscopic annelid we just talked about, really anchoring these specific Fibonacci numbers to their biological traits for easy memorization. Just notice how the lower sequence numbers, 3, 5, 8, and 13, they completely dominate the macro body plan boundaries and the internal organs of the earthworm. Meanwhile, the higher numbers, like 21 and 34, those dictate the super dense ciliary structures of the microscopic protozoa, as well as that one crucial 34th segment boundary in the earthworm. It's all connected. Now, Dr. John Will's research ultimately concludes that this incredibly ubiquitous mathematical pattern, well, it isn't magic. It's deeply rooted in the genetic and epigenetic mechanisms that govern exactly how stem cells divide and differentiate. It basically acts like an anharmonic oscillator. Think of it as a cellular segmentation clock, converting the temporal, time-based rhythms of cell division into precise, physical, spatial boundaries. Which really leaves us with a lingering mystery at the end of this explainer. If the very shape of biological life, from a tiny, single-celled organism twisting in the ocean to the literal heart of an earthworm beneath our feet, if all of that is dictated by a recursive math sequence, are species actively designing their own evolution to adapt, or are they all just beautifully, helplessly following the numbers? Definitely keep that in mind the next time you look out at the natural world. Thanks for learning with me today, and hey, stay curious.